So I wanted to get started with chapter 15, looking at impulse and momentum, and this is just another way of thinking about things. We'll see as we go on and talk about how this compares to work energy and whatnot, but we'll get started with impulse and momentum. And if we go back to Newton's second law, that force is equal to mass times acceleration, and we think about that a little bit differently and maybe say, well, what if we thought about this as the sum of the forces is equal to mass times the derivative of the velocity, and then rewrite that even a little differently, take the derivative of the mass times velocity. That'll have some implications in terms of constant mass and whatnot, but we'll deal with that in a moment. So instead of always having to write this, I'm going to let then this symbol G be equal to the mass times velocity. So I could say that G dot, which is the derivative with respect to time, is equal to the derivative with respect to time of the product of mass times velocity. So I could really say then that the sum of the forces is equal to the derivative of this G term. And we probably want to define this G term where we can say that G is equal to the linear momentum. It's equal to the linear momentum. Or we could say that G, and it's certainly a vector, is equal to mv. Okay? It has units then, if we look at the units on this thing, of newtons times seconds, force times seconds, or pounds times seconds. Okay? Those would be the units on that. Well, with that, I mean, and one requirement on this equation here is that we have constant mass. Okay, that is a lot of good problems fall into that category. So we can say that the sum of the forces is equal to the derivative of the linear momentum. And maybe if I write that out in a form we might recognize from math. So the sum of the forces is equal to the derivative with respect to time of that linear momentum. Okay. And if I integrate both sides, so integrating both sides, I get the integral of the sum of the forces over t. So this is going to go from t1 to t2. That would be equal then to essentially G1 or G2, the linear momentum at state 2, minus the linear momentum at state 1. Or we could say that this is mv2 minus mv1. Okay. And these things take on certain identities. We could say that this is known as the linear impulse. It's a linear impulse. And of course, this is the change in momentum. Okay. So we relate the linear impulse to the change in momentum. We can say then if the linear impulse is equal to 0, so if the linear impulse is equal to 0, or the integral of the sum of f dt is equal to 0, that's another way of saying that, then we can say that we have conservation of momentum. Okay, we have conservation of momentum. So if the linear impulse is equal to 0, we have conservation of momentum. You've probably done some conservation of momentum problems in physics, and we'll do some in here. Maybe we should talk a little bit about how this differs from work energy. Remember that if you, maybe I'll separate this off here. So going back to work energy, if we saw a force over some distance, the area under there was the work, right? So if someone starts talking about force and distance, you're probably going to start thinking about work and energy. Whereas up here, if we look at force over some time, what are we going to think about? Impulse and momentum, right? So that's a good test because a lot of times we get to the end of the term and you don't find a particular problem out of chapter 14 or a particular problem out of chapter 15 and you think, oh, I'm taking this final, and how do I do this? Well, if you're presented in the problem and it's force and distance, you're probably going to be thinking about a work energy solution. If you're presented with a problem and it's force and time, you're going to be thinking about an impulse and momentum. What's one of the reasons we look at impulse and momentum? Well, impulse and momentum is pretty good for collisions because if you look at a collision, usually energy is not conserved. You lose a lot of energy to noise and thermal effects and things like that. But impulse and momentum is usually conserved across the collision, and you can describe collisions pretty well. So you'll see a lot of problems in this section dealing with collisions. Not all, but a lot of them dealing with collisions. And one of the classic ones we'll look at is the ballistic pendulum. Questions so far on that? So if our impulse, if this term here is this impulse term, if that's equal to 0, we have conservation of momentum. That would lead us to the equation you've probably seen before, that mv1 is going to be equal to mv2, and we can do lots of problems with that. Before we get into some of those problems, let me look at another twist on this, and I want to talk about angular impulse and angular momentum. So if we look at let's see if I can draw this. System, we take a coordinate system like this, x, y, and z, and I look at something with a path here, and this, let's say it's a particle or a point moving along. It's going to have some mass times its velocity. Its velocity is in the tangential direction, so that linear momentum is also going to be in the tangential direction. And if I define this with some position vector r from this origin of this coordinate system, if I were to take r and cross it with mv, I could say that this term h naught we'll talk about in a little bit is equal to r crossed with that vector mv. That's going to be a mutually perpendicular vector, which would show up out here as r crossed with mv. And what this is we define this as our angular momentum. Angular momentum, which is really just the moment of the linear momentum. Okay, so the angular momentum is the moment of the linear momentum. I think I'm missing a vector. It's a vector quantity here. If I look at units on this thing, we're just going to add a length component to the linear momentum. So we'll have newtons times meters times seconds. So instead of newtons times seconds, we'd have newton meters times seconds in the metric system. Or in the English system, we would have feet times pounds times seconds. Instead of pounds times seconds, we'd have feet times pound times seconds. And you just go through the crossing. This is a cross product. Of course, as we remembered from our work in statics, the order is important with the cross product. It's not commutative, so it is indeed r cross mv and not the other way around. You'd be off by a negative side. Well, let's take that and look at what we can do with that. Instead of summing the forces, then I'm going to sum the moments. I could say some moment about a particular point is equal to r crossed with the sum of the forces. We've been through that before. Take the forces and multiply it by the perpendicular distance or the component of the distance. And we can say then that this would be equal to R crossed with mv, right? Okay, making that substitution for F. So if I look then at the angular momentum, h naught, being equal to R crossed with mv, we could say that if I take the derivative of this, what's that going to look like? Well, I'm going to use the product rule, and that's going to be the derivative of R crossed with mv plus R crossed with mv dot. Okay, that would be the product, using the product rule to take the derivative of that. And let's see, we could rewrite this. What is R dot? Not quite so far as acceleration. Thanks for jumping in there. It's really velocity, though, isn't it? Yeah. If I differentiate R the first time, I get velocity. If I do it the second time, then indeed I do get the acceleration. So we could say that this is velocity crossed with mv plus R crossed with mv dot. And I'm curious about this one. Essentially, I'm looking at v crossed with v. Okay, it's multiplied by a constant, that constant being the mass in there. But what is v crossed with v? Yeah, 0, isn't it? Okay, so this turns out that the derivative of the angular momentum is really just equal to R crossed with mv. So indeed it does follow that it is the moment of the linear momentum. So I could say then with this, have I seen this before? Yeah, this is just like that thing up there. So I can say that maybe I'll continue working up here, that the sum of the moments about O is equal to the derivative of the angular momentum. Okay. And if I integrate both sides, so integrating both sides, I get the integral from t1 to t2 of the sum of m naught dt is equal to h about some point 2, let's say, minus h about that same point at time 1. Where we get with this piece here, this is our angular impulse. And over here we have the change in angular momentum. And we could say the same thing that we did with the linear case. If our angular impulse is equal to 0, if the angular impulse is equal to 0, then what do we say? We have conservation of angular momentum. Okay. So if this term over here, if that ends up being 0, we have conservation of angular momentum. Questions so far on that?
For the integration of that, is that the angular, is that not h not to maybe adopt about this?
I don't, let's see, do we have that? No, because that was part of what I did. When I integrate this side, I'm left with the integral sum, but when I integrate that side, I get rid of that dot. Other questions? That's a good question. We don't probably, in this class, we're not going to use angular, impulse, and momentum quite as much as linear, but you will use them. Mechanicals are going to go on and do an advanced dynamics class where you'll have more of this. So we wanted to at least touch on it. Well, let's take this all and see if we can do a problem. The one thing, going back to this linear problem, is when we talk about this expression here, this summation. This summation here has a very stringent meaning. It means all, doesn't it? It doesn't mean that you get a mulligan, that you get one, you do a good job, you're a nice person, pleasant looking, so if you miss one force, you're probably okay. No, it means all forces. So that means that a free body diagram becomes very important in this because we have to keep track of every force, because it's all forces, and we also have to account for the direction. We can't just blindly add them up. If some of them are going the opposite direction, we're going to have to account for that. So our free body diagram is going to become more important than ever. Let's tackle a problem then with that. Something like this. So we've got some sort of a ore cart, or they've got some mine material, mine ore or something. We're pulling it up an incline. Maybe it's sawdust. I don't know. Whatever it is, but it's some sort of a cart, and its contents is 150 kilograms. That's going to be a little over 300 pounds. And we're told that as things start out, that it is going down the slope. It's going down the slope here at 4 meters per second. So we're in the metric system. The slope is 30 degrees with respect to the horizontal. And we have this pulley system. We have this cable or rope that's going around this moving pulley fixed to the car, and then up over this, and we're applying this force P to it. And we've got this diagram. And it's worth noting on this diagram that we have the force P, and it's with respect to time. So we should automatically think what? Not work energy, but impulse and momentum, right? Not work energy, but impulse and momentum, okay? And looking at this graph, it looks like P increases from 0 up to a maximum value of 600 over the first, 600 newtons that is, over the first 4 seconds, and then goes to some constant value, maintains at that 600 newtons for the rest of the time. And what we'd like to do then is we would like to ask the question and find the answer when the cart reverses direction. So it looks like this thing's heading back down into the mine shaft, which is not good. We're trying to pull that valuable ore out. So we wonder when it reverses its direction. And then also what its velocity is at t equals 8 seconds. Okay? So presumably somewhere in here, we could say that we have some reversing of the direction. And some students will say, well, how did you know that that happened after 4 seconds? Well, I worked the problem before 4 seconds, and I got some nonsensical answers, which is what you'd have to do. There's no other way of figuring that out. But since we want to keep this as a nice lecture problem, I'm going to tell you my conclusion there and say that it reverses after 4 seconds. Okay? The only way of figuring that out is to try both ways. The other thing is, here at 8 seconds, we'd like to see what the velocity is. Okay. Well, let's see. What can I do? First thing I should do is a proper free body diagram, right? So let me do a proper free body diagram for this cart over here. And let's see, with our pulley system, what kind of force do I have there? I mean, if I cut through here, I'm going to have what? 2 times P, right? Everyone's okay with that? Yeah, that's 2 times P. And then we've got the normal force here, and I'm not going to try and put a normal force at each wheel. I'm just going to sum them up, say I have a normal force like this. And then we have the weight acting to the center of the Earth, so that's 150 times 9.81. Okay, that's the weight. And anything else? See, we've got the force of the cable pulling on it. We've got the normal force, the incline pushing back on it. We've got the weight. I think we're good. Yeah, we're saying there's negligible friction on this. Yeah, good question. Good call. And that's probably not as rash as it might sound. A lot of times with rail cars, you have steel on steel, you can have very low friction. If a rail car doesn't have the brakes on, it's actually fairly easy to move. Now, I wouldn't want to try and move 70 of them like some of the the bodybuilders do or something like that. But one rail car is not too tough to move. So having negligible friction is probably not a bad assumption here. The other thing that I probably need to do in terms of assumptions is I'm going to take my x direction here. So I'm going to say that this is x. And in fact, I'm going to say that this is positive x. And while I'm talking about that, I will say that that is y. So I've taken my direction x up the ramp positive. I've taken y perpendicular to the ramp. So then I can look at the impulse momentum equation and say that, where did we start? We said the integral from t1 to t2 of the sum of f dt is equal to mv2 minus mv1. And I'm going to reduce this. I want to look just in the x direction, because my velocity is in the x direction, so I'm going to look in the x direction. So I'm going to say then that I have the integral from t1 to t2 of the sum of all the forces in the x direction. Okay, so I took the vector off of that. I got the x direction there. Is equal to the mass times essentially the change in velocity in the x direction. Okay, so I'm just looking in the x direction. I can break it up. I could look in the y direction too if I had stuff going in the y direction. So let's go through this. What I'm going to have is, we have to think of this really as the area under our force time curve, right? Is there some area under this section here? Yeah, absolutely. What's that going to be? 1/2 times 4, that's the base dimension of that, times 600. Okay, that's the area of that. But this force is really 2 times p, isn't it? So I'm going to put the 2 there. And that comes from 2 times the p-value. So I've taken care of that piece. Now I have to do this little piece over here. And I'm going to say that this chunk of time here is delta t. Okay. So I'll say that I have delta t times 600 times, and then I still have the 2. Okay, so there's that other 2. So I've pretty well exhausted my concerns with the cable, the 2p value. What else do I have going on? Any other forces in the x direction? Well, I got this distance across this triangle, that's 4. Okay, and then I have this distance, which is 600, and then the 1/2 because it's a triangle. So this is really just the area of the triangle. Maybe we should put the little triangle picture here. That's the area of that. This is the area of that piece. Other questions? Well, I've taken care of this this force here, 2p. The normal force is perpendicular, so I don't have to worry about that. But there is a component of force here that is in the minus x direction, isn't it? So I'm going to have to take, what, minus 150 times 9.81 times, what's that component? Sine of 30? Because if I look at this angle in there, that's going to be your 30 degrees, so I'm going to have the sine of 30. So that's the force. I don't want just the force. I want the time that it acts over. Okay, so how long does this act? 4 for sure. And then what? Delta t. Okay, so I have my force times time. And the negative sign is because I've taken positive x up the ramp. Positive x is up the ramp, and this is clearly acting down the ramp. Okay. So I think we've exhausted the left-hand side of this, and I can set this equal to then the mass. What's the mass on this thing? 150. And that's kilograms, so that's a mass term. And then I'm going to have what? This delta Vx will be what? Velocity 2 minus velocity 1, and that's in the x direction. So what do I have for velocity 2? I'm trying to find when it reverses direction. How will we know when it reverses direction? Yeah, momentarily comes to a rest, doesn't it? So this would be 0, and then I would subtract off this x1. What's x1? It's 4, but it's actually, we have to be careful, it's negative 4, isn't it? Because I have to use the same sign convention on both sides of the equal sign. If I'm taking negative down the ramp and positive up the ramp on the left-hand side, I've got to take negative down the ramp and positive up the ramp on the right-hand side. So this would be minus 4 because it's pointing down the ramp. Okay. So when we go through that, we've only got one unknown. We've got delta t. You can solve for delta t, and delta t turns out to be equal to 2.46 seconds. And had you put the reversing point there, you would have got some odd answer, and that would have been a cue that, hey, you need to try the other side of 4. More than 4, not less than 4. Well, so when is our time for reverse? 4 plus delta t, which is going to be 6.46 seconds, isn't it? So we answered that one. Now the other part we would like to find is what's the velocity at t equals 8 seconds? Questions so far with that? Well, let's try this. This was page, what, 3? Moving on to okay, so see if I can do this. We're trying to find the velocity at t equals 8 seconds. Okay. And there's a couple ways that we can do this. We could go from, and we had to make decisions like this with work energy. We can go from t going from 0 to 8, or we can say that t goes from, 6.46 to 8? Either one of those would work, right? What are some advantages and disadvantages to both? I mean, this is kind of nice because I don't have to worry about the triangle anymore, right? But what am I basing my answer on? Yeah, the previous answer. Okay, so maybe I will leave this for you to do. Okay, you can go back and check this out, and I will go back and do this, so I don't have to base it on that first answer. So in doing that, I'm going to look at exactly the same equation that we looked at before, the integral from t1 to t2 of the sum of the forces in the x direction, dt, is equal to mass times the change in the velocity in the x direction. And again, I can't overemphasize enough, this is all of them. Okay. When we were back up here, I think a lot of people probably would not have put that one in there. Okay. But is that weight, is that a force? Certainly. Is it acting over the 6.46 seconds? It certainly is. So we don't get to exclude that. So I think the left-hand side of this is going to look very similar except for the t value. So as I go through this, I'm going to have a half times 4 times 600 times 2 plus, and now I don't need the delta t anymore because it's going to be what? Another 4, right? Okay. So this one is from essentially 0 to 4, and then over here I'm going to go 0 to 8, So I will have 4 times 600 times 2. And then I'm going to subtract off 150 times 9.81 times the sine of 30. And what do I have to do here? This is going to be 8, isn't it? 4 plus 4, that would be 8. Wouldn't what be where? Okay. Oh yes, my note here is incorrect. This is 0 to 4, and this would be 4 to 8. Thank you. 4 to 8, so this gives me 4 in here, and this gives me 4. And then we've got, yeah. So this one comes around to there, and this one. Yes, thank you. Okay. Now, what's this thing going to be equal to? We've got the mass, which is what, 150, times, then we had the velocity at 2. What's the velocity at 2? That's what we're looking for, yeah. That's the velocity that we're looking for, the velocity at 8 seconds. And then I have to subtract off the initial velocity, which is what? Minus 4 again, okay? So doing it with this one from 6.48 would have been a little nicer. We wouldn't have had this term here. We would have had different times in here, and we would have got to put a 0 there. But again, it would have been based on that previous answer, so we could have propagated mistakes. Well, we have then one equation and one unknown. We can solve that for V, and V turns out to be equal to 4.76 meters per second. Okay. And you can check this out by doing this one. Try this one out. Try this at home. Because home doesn't have an I. Okay. Okay. So 4.76 milliseconds, or 4.76 meters per second. Maybe we should check the units on this. So what if I do a quick units analysis on this? Do they work out? Let's see, what's this term going to be? We had the half and then the 4, that was seconds, times the 600, which is newtons, times the 2, that's just the multiplier, so I have newtons times seconds. What did we have in this term here? We had 4 seconds times 600 newtons. What do we have in this term here? We had 150 kilograms, 9.81 meters per second squared, times 8 seconds. This was a kilogram meter per second squared. That is a newton, isn't it? So newton times seconds, that's good. This was minus, this was plus. Then over here we had 150 kilograms. Okay, and inside the parentheses, this was what, 4 meters per second. I got my answers in meters per second, so I would have meters per second. Oh, this doesn't look so good, does it? Well, what if I work on this a little bit? If I take kilogram meters over a second and I multiply by a second over a second. Can I do that? Second over a second is just 1, isn't it? So now I have kilogram meters per second squared. What's that? That's a newton. So I have a newton times a second. So the units do work out on that. And I was probably a little bit careless with the units. Maybe I should have written them in here, but I knew I was going to get a very long expression, get it to fit on the screen. I omitted those, but you have to be really careful, particularly when you start getting into the English system and you start mixing inches and feet and things like that. You need to be very, very careful. Well, to sum up this problem, the thing that I would tell you, the most important thing is the free body diagram. Because when you do the forces, this summation here, this is all of them, and you got to get them in the right direction. Okay. So that'd probably be the biggest tip that I would give you in this. Questions with that? Well, that gets a good starting point. We haven't done a conservation of momentum problem yet. We can look, of course, a very classic one is you have something firing something. So we've got the, draw a quick picture of a gun here. Kind of a rough model. Looks like someone might have whipped that out in a prison cell or something. But anyway, we've got the velocity of the bullet or the projectile here, and we have the mass of that bullet or projectile. And then we have the recoil velocity, don't we? The velocity of that gun and the mass of the gun. And we'll find out with some problems like this that sometimes the larger, uglier looking, the dirty, hairy, so to speak, kind of guns may not be actually that bad, because with this large mass term here, what's that do to the recoil velocity? It reduces it, doesn't it? Okay, and that's a very classic conservation of momentum problem. We'll look at cars moving on a barge too. You take a barge and look at a car moving on that barge, and the barge then going the other way. That's another classic conservation of momentum problem. People changing positions in a canoe or a toboggan, I think you've got a homework problem with that. So we've got a lot of work in the future with very classic conservation problems, and that's where we'll go after the examination. So take care till then.